little countdown. We will hit PowerPoint once it finishes. There we go. From current slide, and Lindsay's here. All right. Anyone else come in since the call roll? All right. There's a bunch of announcements. I'll try to get through them as quickly as possible. And I am not at all certain what this is. It sounds pretty good. The name of it is First Call Quality. It's First Call Quality Services. They're based out of Indianapolis, Indiana. There's a phone number, 800 number you can do. But the One-Stop Career Center here at Lawson State Community College, just over here in the Millsap building's that way, on the other side of this building, is taking applications for the job fair. Now, what they're looking for are quality inspectors, $11 an hour, team leaders, $13.50 an hour, and when? Tuesday, March the 6th. Where? At the One-Stop Center, Career Center over here in the Millsap building. And the time is 9 to 1 o'clock, and benefits are available. Okay? It sounds like a one-day deal. Usually they don't do benefits for a single day, but maybe they're going to hire you on to do it at various places. I don't know. I haven't made this out yet. Okay? Applicants must have a clear background check. DL, I don't know what that stands for. HS is high school. Say again? Driver's license, you got it. Driver's license, high school, diploma, or GED, and automotive manufacturing experience preferred, okay? Not required, but preferred. If you want to contact someone, Miss Brenda Thomas is here at Lawson. That's a Lawson number, or Miss Dorothy Henry. Maybe Dr. Dorothy Henry, I don't remember. And she's here at Lawson. Both of these are Lawson phone numbers. So if anyone's interested, or you know of anyone that might be interested, get the information here and go for it. All right. These are not necessarily in order because they kept coming in. All right. There is an organization that's it deals a lot with National Science Foundation. It's called QEM, and it stands for Quality Education for Minorities, I think. I don't see it on here. They just call it out themselves as QEM. Okay? Has decided to extend the deadline for applications to QEM's Talent Development and Innovation in Sciences, quite a mouthful, summer internship program to March 2nd, which is this Friday. Okay? The Talent Development and Innovation in Sciences, that's TDIS summer internship program, is a 10-week paid, P-A-I-D, paid internship. Second, right? Yeah, Kelsey, got it. Okay. All right, thank you. Anyone else coming in, Sister Caldwell? Okay. A 10-week paid internship includes housing. You don't have to provide your own housing. Includes housing for interns in Washington, D.C., conducting research projects for the National Science Foundation. QEM TDIS students or interns will also be engaged in a variety of professional development activities and can receive additional support from QEM to attend conferences, workshops, and trainings throughout the following academic school year. So even after you're through with the summer thing, you can still receive funds from them and support from them. Let me get Chris Mark here before I forget it. Okay. Anyone? Yes. And here's Shayla, right? find you on the page here. All right. Okay. So it says, please encourage your students, consider yourself encouraged to learn more and apply at, and it's a website, www.qem.org/QEM-internships. If you have any questions, comments, concerns, you can contact, and they have a direct contact number. Apply for internships, quality education for minorities. There it is. I knew it was on the page somewhere. Tribal colleges and universities, TCUP, that's for the Native Americans, Science Education Focused Summer Internship. The internship is designed to provide students with an opportunity to learn more. And then also, I know that HBCUs are also encouraged. And then they have a couple of testimonials from students who did it last year. So if you want to see this, it's up here. Friday's the deadline, so get moving on it if you're interested. Now, I announced, I think this to you last time, there are scholarship opportunities, presidential scholarships at both UAB and University of Alabama, Tuscaloosa. The deadline for them is Thursday. That's the 1st. That's the day after tomorrow. So if you haven't started on that, please get moving on those. Math team's still looking for anyone who wants to participate. They're having a lot of fun doing it. They meet Fridays at noon, not this Friday, because Mr. Ashley is going to be at the same meeting I'm going to be at up in Jasper, and Mondays at 3 over on the Birmingham West Campus. C100 is the room number. Okay? That's over with. The tutoring schedule, I think I read to you before, for the Space Center here on this campus, and I told you about the one in the Student Support Services and the ones on both campuses. Okay? Now, there was a question earlier. I have a meeting that's been called tomorrow from 2 to 4. However, I have a class from 2 to 3:15. But as soon as that class is over with, I'm moving to the Bethel Hall building for the last 45 minutes of the meeting, and I'll be there, so I won't be in my office until after 4. Taylor's here. Just got to find you. There you are. All right. Okay. There's 2 more, okay? The dean has called a dean and chairs meeting for Thursday, okay? This will be at 2 o'clock, and it says it goes till 5. I've requested permission to leave early because I've been invited to, because I'm speaking at the meeting on Friday, been invited up there on Thursday evening at 6. So I've got, if I'm going to accept the invitation, I've got to leave by 4:30. So basically Thursday afternoon after 2 o'clock, I'm not in the office anymore. Friday, I'm not on either campus on Friday. We're at meetings in Jasper, Alabama. Okay. And are any of you graduating this term? You are. Okay. Okay. If you are, do you know about the meetings for graduation? Good. There's one in the evening on the Birmingham campus Monday, on this campus Tuesday afternoon at 1:30, over here in Ethel Hall Auditorium, and then back on Birmingham campus on Wednesday at 1:30 in the afternoon. So I've got that information. If you know of anyone who's graduating, please share that with them. Okay, anyone else come in since I called roll? Any questions about anything I just said? Let's get moving. Okay. Any questions on math? Anything we've done in here so far? All right. This is the last section we're going to do in Chapter 1, Functions in the Graphs. Okay. And if you didn't believe it, they believe in graphs. Okay. And 1.9 is inverse functions. Okay. What the objectives here are, we're going to find inverse functions informally, which almost I think is a kind of waste of time. but if it helps you understand it a little better, that'll be maybe about it. And verify that two functions are inverse functions of each other. Yes, we'll be doing that because that's how you check and make sure you got them right. We'll use graphs of functions to determine whether functions have inverse functions or not, which leads to the horizontal line test. To determine if a relation is a function, we use the vertical line test. To determine if the function has an inverse, we also use the horizontal line test to determine whether the functions are one-to-one. If they're not one-to-one, if they fail the horizontal line test, they're not invertible. They do not have inverses. And we'll find inverse functions algebraically. Yes, that's the good stuff. Okay. But then we'll go back and use the other stuff. So let's talk about what inverse functions are. Now, remember we can represent functions in a variety of ways. You can talk about them. You can set them as sets of ordered pairs. You can graph them, and you can write equations for them. Okay, so there's lots of ways you can represent a function. Okay, one of these ways is ordered pairs. So let's say we have this function, f of x is equal to x plus 4. Is that a function? They say it is it? What kind of function is that? Yes, it's a linear function. And linear functions pass the vertical line test everywhere. Unless, of course, it's a vertical line and then it fails it. Okay? But if it's not a vertical line, and this is not, because it has a defined slope, 1, okay? So this function takes values. Now we're going to have a designated domain, an explicit domain. Its domain is 1, 2, 3, and 4. Pretty simple, right? Okay? If you use x, 1 for x, what's your y? 2 for x? 3, 4, 8. Okay. This is your input set. We call the input set. Input set. Starts with a D. Domain, okay. And this would be the range, the output set, okay. And that can be written as follows. This function you can express as a set of ordered pairs because you have a limited domain, limited range. Here's that function. Here's the mathematical expression for it. Here's the ordered pair expression for it. 1, 5, 2, 6, 3, 7, and 4, 8. We just said that, right? In this case, now, here's what we're going to do. If you interchange the first and the second coordinates of each of those ordered pairs, you form what we call the inverse function of f. Okay? So if we just flip these two and make that 5, 1, 6, 2, 7, 3, and 8, 4, you now have a new function. And that would be the inverse function of f. Inverse function of f. Now, here's our representation for it. F to the minus 1. Now, that does not mean 1 over f. If that was a variable to the minus 1, or a number to the minus 1, that would be 1 over the value, 1 over the variable. This is not a number or a variable, this is a function. A function to the minus 1 means an inverse function. So we're using a similar notation, but because we're talking about functions, it means something completely different. Okay? Now, I'm just going to see if you sort of are following. Can you guess what that inverse function would be? That takes 5 and makes it 1, that takes a 6 and makes it a 2, that takes a 7 and makes it a 3, that takes an 8 and makes it a 4. Yes, if you have f inverse is x minus 4, you've done exactly that. And guess what? This is nothing too new. Because when you first started kindergarten or elementary school, one of the first mathematical operations you did was addition. You had to learn all those addition tables. So long ago for me, I hardly remember it, but I know I had to, okay? But then, once you thought, okay, I'm through with math. No, you're not. They turned it around in undid addition with the operation of subtraction. Okay, so then it wasn't too bad because you could always go back and check it with addition. Okay, finish with nope. Then they had you learn multiplication. Okay, all those tables, you know, and the flashcards, all that kind of stuff. I don't know what they did in your day, but that's yeah. And then when you finally got those down, you undid it with the division. Okay, so you did an inverse operation. Well, these are inverse functions, so it's no surprise that you get the inverse of f. As you said in this case, all you do is change the addition to subtraction, and you got it. It's not always going to be that simple, but on very simple functions, it will be almost that simple. Okay? It is a function from the set B. Now, what is B now? If you flip all those around, what is your set B? Like this. That becomes your domain of the inverse function, and set A becomes the range of the inverse function. So the inverse function flips to domain and range. Okay? So there is some flipping going on, it's just not like that. Okay? It's like this. Okay? Now, this is a function, the inverse function, that goes from set B, now becoming the input, the domain, to set A, which was a domain, now becomes a range, and can be written as follows, and you got it absolutely right. F inverse of x is x minus 4. It takes the 5 from B, subtracts 4 from it, becomes a 1 from A, 6 from B becomes 2 from A, 7 from B becomes 3 from A, and 8 from B becomes, hard to say, 4 from A. Notice that the domain of F is the same as what the range of F inverse and vice versa, as we just said. Now, down here we have what we call a mapping display. This is another way to express a function. Okay? Kanisha, right? All right. I know you're in here. I haven't kicked you out. There we are. Okay. I think they kicked you out yet. Okay, got it. All right. Anyone else come in, Sister Caldwell? Okay. So this is a mapping. Okay? And this shows x being the domain of f, and when you operate on it with f of x is x plus 4, you get the range, which would be the values for the y, or the f of x. But this then turns around and becomes the domain for f inverse, which takes you back, and when you do f inverse on this, you go back to your x that you have there. Okay? Notice that the domain, I think we've said all that. Also note that the functions f and f inverse have the effect of undoing each other. Just like subtraction undoes addition, an inverse function undoes the previous function. So if you started with an x, operated with f, then operated on that result with f inverse, you get your x back again. Okay? That's the key. We'll hit that in just a few minutes. In other words, okay, maybe hit it right now. When you form the composition of f with f inverse, or the composition of f inverse with f, remember that? It was like 3 days ago, 4 days ago, it's a long time past, yeah, but we did compositions. You obtain this identity. F operating on f inverse, we're going to use the ones we just had, your f inverse was x minus 4, remember? And f operating on x minus 4, remember what f was? It was whatever was in here, x plus 4. But now we're operating on x minus 4, so it's x minus 4 plus 4. Ha! What you wind up with? X. Okay? Now do it the other way. F inverse operating on f, remember f is x plus 4, so f inverse was whatever is inside here minus 4. So inside here is x plus 4 minus 4. That gives you x. Now, I know it was last Thursday. Lots have happened since then. But remember, generally, when we did f operating on g, we got some answer. And then when we turn around to g composed with f, you usually got a different answer, right? In this case, we don't. Remember I said there will come some special cases where they're not different. This is one of them. In fact, the main one. Gavin, right? Okay. Anyone else come in, Sister Caldwell? Okay, so that's going to be the test. If you think you have inverses of each other, compose one with the other, see if you get an X. If you don't get an X, it's not an inverse. But don't stop there, then compose the second with the first. If you also get an X there, yes, ding, 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 you have an inverse. Okay. All right, here's example 1. It says, find the inverse of f of x equal 4x. Anyone want to make a guess of what that might be? You got it. F inverse of x would then be 1/4 x, or x divided by 4. Either one you want to do it, okay? Now, we found it, or at least we think what it is. Let's verify it. Let's first do f of f inverse of x. And what do we plug in first? The innermost, okay? So that's f of, and what's f inverse? No, f inverse is 1/4 x. And it's all right if I write it as x over 4. It just takes up less effort on my part. X over 4, is that okay? Okay. Now let's operate on that with f. Well, here's f up here. What does it say to do? Start with a 4, and then multiply it by whatever's inside the parentheses. And what's inside the parentheses? X over 4. And what happens if you do that? The 4's divide away, and you're left with x. That's looking good, isn't it? But we still have to do the other way. And what's the other way? F inverse of f of x. Okay? And that would be, where do we begin? With the f of x. So you do f inverse of f of x is 4x. And what does f inverse tell you to do? Okay, yeah, divide. You take what's in the parentheses, okay, right here in the parentheses, and that's x over 4, and, I'm sorry, it's 4x. What's inside the parentheses, looking at the wrong parentheses, it's 4x, and then you divide that by 4. And sure enough, what happens? The 4's divide out, and you're left with x again. Ding, 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 ding. That means these are inverses of each other. Again, that was pretty simple because they're just single operation functions. Most of the time, you can almost guess those. Okay? We did. Okay, in fact, guess those. All right, there's a checkpoint there, which is a very similar problem. Please do that, especially if this is a little fuzzy. Oh, but before that, let's clear my chicken scratch here. And let's see how they did it. The function f multiplies each input by 4. To undo that, we'll need to divide each input by 4. That's exactly what your reasoning was, I guess. So the inverse function for f of x equal 4x would be f inverse being x divided by 4. Good guess anyway. And then to verify it, we first do f of f inverse. And f inverse was x over 4. F said take what's inside the parentheses, multiply it by 4, and you get 4 times x over 4, and that, of course, multiplies to be x. But to do it the other way, f inverse of x, f inverse of f, then you do what the innermost function is, 4x, plug that into f inverse, which is x over 4, okay? So you take what's in the parentheses, 4x, and divide it by 4, and sure enough, you get x again. Got it. These two are inverse functions of each other. All right, so that's illustrative, but we haven't really defined it yet. So here's the definition. Let f and g be any old two functions such that f of g of x is equal to x. So they're not any old two functions. That's pretty specific. For every x in the domain of g, and we want g of x, g of f of x, to be x for every x in the domain of f. You see, there's a difference here. These x's live in g to begin with. These live in x, okay? You can think probably of some functions that would have one domain for this, but a different domain for that. But as long as both of these are true, under these conditions, the function g is called the inverse function of the function f, and the function g is denoted by f inverse. When you see that, don't say, well, f inverse is the best way to say it. So f of f inverse, that's f of g, is equal to x, and f inverse of f, which is g of f of x, is equal to x. The domain of f must equal to the range of f inverse, and the range of f must be equal to the domain of f inverse. They just exchange. Okay? Make sense? All right. Now, this is what I've already said, so they're going to emphasize it now. Do not be confused by the -1 as the superscript. Okay? That means the inverse of f. Okay? In this text, whenever you see a function with a superscript -1, it's always referring to the inverse function, not to a reciprocal of f. If you want reciprocal of f, put 1 over f. Okay? That's what we do. Okay? Hey. Brianna Wright. Walker. Welch. We already got Walter here. Okay. All right. Good deal. If the function g is the inverse of the function f, then it must also be true that f is the inverse of g. So if you have one function has an inverse, the other function has that function as an inverse. For this reason, you can say that f and g are inverse functions of each other. Okay? They always occur in pairs that you can do it either way. Okay? Now, they're skipping example 2. So let's go back and do example 2. And, all right. Is it Kayla?
No.
Huh?
Amber.
Amber. Okay, got it. There you are. Okay. Couldn't find you in here. Okay. Anyone else come in since the call draw? Okay. So let's do example 2. The one they showed on the slides was really, really, really easy. This one, glad that they didn't just ask you to do it, but what they're asking here is, here's a function, f of x is equal to 5 over x minus 2. Okay? And what they're asking is which of these two functions might be the inverse for f of x. Either g of x, which is x minus 2 over 5, or h of x, which is 5 over x plus 2. Now, does anyone want to hazard a guess? G or H?
H.
Okay, the guess was H. We'll see. How do we determine which of those is the inverse of f of x? Say again?
Set them equal to each other.
Not equal to each other. Do the composite of each other. Compose them with each other. So we first do f of g of x. Now, if these are inverses of each other, what did that better come out to be? X. Okay? Let's see if it does. What do we plug in first? You plug in the g of x. Okay? And so you do f of, and g of x is x minus 2 over 5. The one that has been voted out. Okay? Let's see if that was correct. Well, what does the f of that mean? Well, your f function says start with the number 5 and divide it by what's in the parentheses. And what's in the parentheses here is x minus 2 over 5. And then subtract 2 from that. Kind of looks like a mess, doesn't it? That's what in some texts they call complex fractions. I don't like that name. I like to call them complicated fractions. What you do with those is find the least common denominator of all the denominators in both the numerator and the denominator. Of course, the only denominator you got is 5. So let's multiply 5 times the numerator and the denominator. Because 5 over 5 is what? 1. And when can you multiply by 1? Anytime you want to. It doesn't change the value any. So let's multiply the numerator by 5 and the denominator by 5. Okay, because that's going to be 1. Okay, so the numerator becomes 25. Now, when you multiply this, you're actually multiplying this by 5 when you distribute, and you're multiplying this by 5. Multiplying everything by 5. Here, your 5's go out, and that leaves you x minus 2 minus 10. Okay, that gives you 25 over x minus 12. Now, do you think there's any way in the world you can make that become an x? Not that I can think of. So, no, not it. So, if it's not becoming x here, don't even bother with g of f of x. Probably not going to happen either. This is not x. This is not equal to x. Whoa, where did that come from? Okay, not equal to x, not the inverse. Okay? Well, let's try the other one, the h of x, the one, I keep forgetting your name. Say again? Kendrick, one that Kendrick suggested. So what do we try first? F of h of x. And what will we do there? You plug in the h of x, so that's f of h of x is 5 over x plus 2. Okay? And you plug that into your f, which is over here. And what the f is you start with the number 5, divide that number with what's in the parentheses, which is 5 over x plus 2, and then subtract 2 from that. Right? The x minus 2. What's in the parentheses here, minus 2. See? Okay. Fred, right? Okay. All right, good deal. Anyone else come in since I called roll? Okay. So let's start working on this. Now, I just threw the parentheses in there because to let you see that is your replacing the x. Okay? That was what was in parentheses here, so I put it there. But really, that's not doing anything for the problem, is it? So I'm going to now erase those parentheses because they really just was to help you see. And now what do you notice? 2 minus 2 is 0. So that disappears. And this then becomes 5, and that's a dividing line, so let's write that as divided by 5 over x, right? And how do you do that? Yes, 5 times x over 5, and what happens there? The 5's go out, and you're left with an x. Yes, that's what we were looking for. Have you completely proven that this is the inverse? You have to do it the other way. So we need to do h of f of x. And what's your f of x? Well, I mean, that's the one you put in first. So h of f of x was 5 over x minus 2. Right? There it is. Okay? Plug that in. Now with h of x, which is over here, it says start with 5, divide it by what's in the parentheses, 5 over x minus 2, and then add 2 to that. Right? That's what h tells us to do. All right. Now, again, let's take this division and write that as 5 divided by 5 over x minus 2. And then we're going to add 2 to it. And this would be the same as 5 times x minus 2 over 5, right? Now the 5's go out, and plus 2. You have x minus 2 plus 2. The 2's add to 0. That also gives you x. Sorry, I skipped a bunch of steps at the end because I was out of board space. You see how it works? Yay or nay? All right, good deal. So that was example 2. If you look at the book and follow it, you'll see it's there. They did it pretty close to the same way we did. They sort of skipped a few steps, I think, but, it came out the same. There is a checkpoint there, so if that one gave you a little bit of issue, please do the checkpoint as soon as you can after class. All right. Then, any questions? Let's move on to the graph of an inverse function. They love graphs, don't they? All right. The graphs of f and its inverse f inverse are related to each other. They're third cousins twice removed. No, okay. If the point, now here's the key. Remember in our first set of ordered pairs, what did we do to get the inverse? Flip them. That's going to be important in the graph too. If the point AB lies on the graph of x, then guess what lies on the graph of f inverse? Okay. BA, okay. That, never mind, we won't go there. Okay. And vice versa, right? Okay. That means that the graph of f inverse is a reflection of the graph of f, not over one of the axes, but over the identity function, y is equal to x, because you're just flipping the variables. Okay? Now here's a function. We all know what it is. It's just some strange looking function. Here it is. There's your f of x. No, there's f inverse. Here's your f of x. Okay? That's a function. Okay? It's really rapidly getting in dangerous territory here because it's almost failing the vertical line test, but for as far as it goes, that's a function. Okay? Now, here's the value a, that's on the x-axis, and there's the value b on the y-axis. If you flip those and make this b on the x-axis and the a on the y-axis, here's your point. And that's exactly a reflection across the identity function. Y is equal to x. Okay? And every point does. When it crosses the identity function, both of them cross at the same point. When they get close, they're getting close at the same point, but when they turn away, so they're exactly opposite reflections across the identity function. And here's something else to note. We'll do this a little bit more later, but we're going to do it right. I'm going to mention it to you now. What kind of function is f? You notice about f of x is always increasing. And look what f inverse is. Still always increasing. So if f is increasing, f inverse is increasing. And vice versa. Okay? That you aren't expected to know yet, but I wanted to point it out since we had such a nice graph there on the board. Okay, so here's example 3. Sketch the graphs of the inverse functions f of x equal 2x minus 3, and f inverse is equal to 1/2 of x plus 3 on the same rectangular coordinate system, and show that the graphs are reflections of each other in the line y equal x. Okay, now, the cynic in me would be, wait a minute, are they really inverses of each other? So I would do f of x, f of f inverse and f inverse of x and make sure. Let's just take their word for it, because otherwise it's going to take too much time. Are y'all okay with that? I'm sorry. You are? Oh, y'all are so understanding. Okay. So we'll assume they are inverses. How would I graph f of x is equal to 2x minus 3? Let me tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6. Ooh, ugly, ugly, ugly. Okay. Really ugly. Okay. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4. Okay. So, how would I graph f of x equal 2x minus 3? Oh, this is going way back. Say again? A little out. Okay, what variable would you like to plug in your variable?
1.
For what, x? Okay, when x equal 1, you're going to be somewhere over here. And what do you have? Say again? I can't hear.
So we'll get after that?
Yeah, when you plug in a 1 for x. I don't think so. I don't think so. Plug in a 1 for x. Negative 1. Okay, there's the point right there. You see that? Okay. Give me another x. 0. I love it. What would you get then? Negative 3. There it is, right there. You want to give me another one? Negative 1. What would you get? That's your negative 5. So that's going somewhere way down here. Okay. Now, that's certainly one way to do this. How I tend to graph a function like that is say, what kind of function is it? It's a linear function. And when you write a linear function in function notation, f of x, which is? F of x is always y. Y is equal to 2x minus 3, right? What form is that in? Y is equal to 2x minus 3. Slope-intercept form, where 2 is the slope and negative 3 is the y-intercept. So first thing I'm going to do, plot the y-intercept right there, negative 3. And then do a slope is 2, so that means up 2, that's rise for 1 to the right. Up 2 for 1. Okay? See, I'm really lazy. Okay? Up 2 more and right 1. Up 2 more. I'm getting lost here. Up here and right 1. Somewhere about here. Okay? And I'm really struggling here. Up 2 more and right 1. Something like that. And you can go down 2 and left 1. And that's also, yeah, get out of there. Okay. That's not a very good straight line, but you get the general idea, right? Okay. Now, this one doesn't work quite as nicely. But let's write that in slope-intercept form. What would that be? What would you have to do to get that in slope-intercept form? Distribute the 1/2 across. 1/2 x plus 3/2. Now, I don't like that as much, okay? Because the y-intercept is 3/2, which would be up here somewhere. And then if you do your rise and run, they're all fractions. So what I do on this one, so so I can start on a tick mark somewhere, is what the, okay, now think of this as y is equal to 1/2 x plus 3/2. Now, if I were going to pick an x, if I was going to pick a number to multiply the right-hand side by to make it look nicer, what number would you choose? 2, okay? So let's multiply both sides by 2. That's a legal move in most states, right? Okay, so that would that be 2y is equal to x plus 3. Okay? Now that I've done that, a very easy point will be put y equals 0 and see what your x becomes. What would it become? Say again? -3. There's your x-intercept. So when y is equal to 0, x is -3. There I've got a point, don't I? Okay? Now go back to this one and do your slope of 1/2. Okay? That's up 1 for every 2 to the left. Up. I should do this in a different color. What color would you like? Pick a color, huh? I don't want to use red yet. Pick another color. Huh? Yellow. Okay, she likes yellow. Okay. All right, it may be hard to see, but let's do it. There's one, then up 1, 2 to the right. Up, can you see that? Up 1, 2 to the right. I think we're right there. Up 1 and 2 to the right. Somewhere in there. And you keep going, or down 1 and 2 to the left. This is where my scale got all squirrely. Something about like that, and then like that. You know. So you get the idea. This line is like this. I didn't draw the line too well. Okay. Here's why I didn't want to do red. Because usually they reserve red for your, yes, your one-to-one, not one-to-one, identity function. Oh, they usually do it dotted too. I'm sorry. I didn't dot it. I should have dotted it. But you see, there are reflections across the line y is equal to x. That's what this is. Y is equal to x is that red line here. I should have dotted it. I meant to. I forgot to. See how it works? And sure enough, f is what kind of function? Increasing. And f inverse is increasing. And where they do cross each other, it's on that identity function. And then they keep on track. Make sense? All right. So there is our rendition of it. Let's see if they can do it almost as neat as mine, okay? Ah, they just throw it up there. Here's the function f. They put in gray 2x minus 3. They didn't put the tick marks very well. 0, -3 is your y-intercept. And then you can do up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1. Or down 2, left 1, down 2, left 1. Yeah, it keeps on going. And then, I don't know if they started here, but I started with -3, 0 from our x-intercept of that equation once we had fiddled with it a little bit. But we saw that had to be the x-intercept, and then the slope was 1/2. So that's up 1 for every 2 to the left, 2 to the right, up 1 for 2 to the left, right, up 1, 2 to the right, up 1, 2 to the right, and so on. Or down 1, 2 to the left, down 1, 2 to the left. -2 over -1 is still 2. I'm sorry, -1 over -2 is still positive 1/2. So there's your graph. And here is the dotted red line that I forgot to dot. Okay? That connects the two. Reflects the two. It appears that the graphs are reflections of each other. You can further verify this by this reflective property by testing a few more points on each graph. Now, they also labeled their numbers, which is a good thing to do too, because you see this is -1, -5. Well, here you have -5, -1. There's 0, -3, -3, 0. There's 1, -1, -1, 1. 2, 1, 1, 2, 3, 3, 3, 3. You know, and they keep on going, and sure enough, they reflect each other. You reverse the x and y coordinates and you have it not. Make sense? Okay, good deal. So, here's what I was just saying, they're saying here on the graph. Notice that in the list, the point AB for f of x is the same as, corresponds to BA f inverse. And the cards at -1, -5, -5, -1, 0, -3, -3, 0, 1, -1, -1, 1, 2, 1, 1, 2, 3, 3, 3, 3, and they keep going. Anything, if you find an x and plug in here, whatever you get for y, plug in there, and you'll get that x back again. Just like we did on our verification. Sorry, I've got hiccups. Okay, they're skipping example 4. So let's back up and do example 4. Let me get my pen color back. Okay. Verify graphically that the function f of x is equal to x squared. Now this is only true when x is greater than or equal to 0. Okay, now that's not quite true, but for our case here it will be. And g of x, which is the square root of x. Okay? It says verify graphically that these functions are inverse functions of each other. You know, I wouldn't even mess with graphically, but they want us to see it, so we're going to do it. Okay? Now, since your x is always greater than 1, they told you that for f. What do you know about g? I mean, greater than or equal to 0. This one also is greater or equal to 0, because you can't take the square root of a negative number. So in both of these, your x's are going to be positive. And by the way, you square any number in the world, especially positive numbers, you're going to get positive answers. So your y's are going to be positive here. And you take the principal square root of any positive number, that's going to be positive. So your x's are positive and your y's are positive. So we only need to graph the first quadrant. So let's come down here and graph the first quadrant. I mean, we can take out a little bit, but we're only going to go there. So you give me some values for your f. I probably should do different colors. You want the same colors we used before or something else? Green, okay? Green, green, it's green, they say, on the far side of the hill. That'll be G because it's green, okay? Green starts with G, okay. All right. So let's start with F and plot on F, okay? Give me an X. 0, and what's your F? 0. Give me another, oh, let me tick off a few points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And going up, 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay? Give me another X. 1, and what do you get? 1. Okay, give me another X. 2, and what do you get? 4. Okay, give me another X. 3, and what do you get? 9. Okay, I think that's as far as I can go on this graph. So here's what it looks like. Y'all know what the shape is? It's not a line. It's a parabola. Half of a parabola. We only are sticking with the x is greater than or equal to 0. That's a parabola. Okay? Now, let's do G in green. Okay? Give me an x. And what you get? 0. Square root of 0 is 0. Give me another x. 1. Square root of 1 is 1. Give me another x. 4. Good choice. And what's the square root of 4? 2. Another one. All right, that would be 5, 6, 7, 8, 9, and that would be 3. Okay? And I don't think I can get to a 16. So that's going to be your square root function, which is what? The top half of a sleeping parabola, right? Parabola on the edge. And guess what our identity function is? That's what I'm going to do in red. If I can get red to come up, that's your, see, this time I'll remember to dot it. There's your identity function, right? And sure enough, they sure look like they reflect across it. Now, I may not have drawn it too well, but my scales are a little squirrely, but not even very straight. But you get the idea, right? So, sure. To me, that's not a verification. It makes you feel warm and fuzzy about it, but especially when you draw as poorly as I do. I mean, that doesn't verify anything. But at least it makes you feel like you're heading in the right direction. All right, any questions? Any? Okay. All right, next topic here, next objective here. One-to-one functions, okay? Now let me tell you, because I know you're going to run into these later and I can't pull it out of you. So here's going to be my clue to you when I say, what do I mean? Yeah, one-to-one. Okay, that's why I'm going, when I ask you a question, then if I give you that signal, you'll know the answer, right? All right, one-to-one. Okay? Here's what we mean. The reflective property of the graphs of inverse functions gives you, before we do this, I'm going to back up a little bit to my pretty drawing here. Now, for this function, why did we only take the top half of that sleeping parabola? Why didn't we include the bottom half? Because what? It's what? Yeah, but you can't have the negative square root of x. That would be fine. You can't have the square root of negative x. You can have the negative square root of x. But what's the problem with taking the bottom half with the top half? It's what? That is? Say again? No, okay. Your domain can't be less than 0. Yeah, you can't have a negative x here. But you could put a minus sign in front of that and do the bottom half. Why don't we include that with this as a function? Vertical line test fails. It's not a function because the vertical line test fails. Remember the vertical line test? I know it was a few weeks ago, but still pertinent, right? Okay, so that's why we had to say only g of x principal square root. Okay? Now, if indeed we had this, that would then have put this one over here. Now that would be a function here, wouldn't it? But you see, you can't take that and reflect it across the x-axis because then it wouldn't be a function anymore. So that's why we had to say x's for this one also have to be greater than or equal to 0. Okay? So, that reflective property of the graphs of inverse functions gives you a geometric test for determining whether a function has an inverse function. That is the horizontal line test. Because anything you reflect across the identity function has to still be a function. So if this one had to pass the vertical line test, that one has to pass a horizontal line test. So the horizontal line test for inverse functions, a function f, has an inverse function if and only if no horizontal line intersects the graph f at more than one point. And you see, if we had tried to do this function and not included this on it, had this go up here, the parabola on the other side, not a one-to-one function, it could not have an inverse. Because if you try to reflect that over it, that wouldn't even be a function. Right? So, the function for it to have an inverse has to be 1 to 1. That's why we restricted this to only positive values. That was already restricted just by the nature of the function, okay? But because it was, then its inverse can only be this one. It couldn't be over here, okay? So, all right. If no horizontal line intersects the graph at more than one point, then no y value is matched with more than one x value. It can't be. So therefore, though we already knew that no x could be matched with more than one y, vertical line test. Now no y could be matched with more than one x, horizontal line test. That means you can only have one x for any one y and vice versa. So therefore, we call these one-to-one functions. One-to-one functions. They always are going to be that way. Okay? So a one-to-one function, a function f is one-to-one. Each value of the dependent variable, the y, corresponds to exactly one value of the independent variable, x. So that means horizontal line test can only strike once. Okay? A function f has an inverse function if and only if it's a one-to-one function. This is the other way I'll say it. When I do that, one-to-one. Okay? If you don't get that, then I'll put the 2 in the middle. Okay? So, all right. Has to be. And that basically is the first thing we got to check when we're going to see if it's an inverse function or not. Is it a one-to-one function? If it has an inverse or not. So let's consider functions. Here we have a table. This is a lot like your ordered pairs. Here's f of x is equal to x squared. That looks sort of familiar, doesn't it? The table on the left is a table of values for f of x equal x squared. X is here. F of x, which is x squared, y is equal to x squared there. The table on the right is the same as the table on the left, but we've exchanged the variables. So when x is equal to minus 2, square that, you get 4, negative 1, 1, 0, 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Okay? That's a function, right? For any x, you only get one y. Is it a one-to-one function? For any y, do you only get one x? There's a minus 1, there's a plus 1. Not a one-to-one function. Because when you switch the order, your x and the y, if you did have an inverse, then this becomes 4 negative 2, 1 negative 1, 0 0, 1 1, 4 2, 9 3. So here you have the same x's, different y's. Not a function. Not one-to-one. Okay? So this function, as written, cannot have an inverse. If you restrict the domain either to the minuses or to the plus, yes, but not with the whole function. Okay? I hear rustling. Does that mean anything? Okay? The table on the right does not represent a function because x input x equal 4. You get either y equal minus 2 or plus 2. So therefore, f of x equal x squared is not a one-to-one function, does not have an inverse with the full domain. All right, we'll begin next time with example 5. Let me give you a few homework exercises. Those will be any of the odds 7 through 13. All those odds are in calcchat.com, 9's at CalcView. 15 or 17 or both. 15's at CalcView, both of them are CalcChat. Do number 19, that's only at CalcView. And the rest of those we'll do next time. All right. Good deal.
Are you teaching Math 113 this spring?
This spring?
Yes, this spring, like the summer break.
Oh, in the summer. Let's see, am I? I haven't made out the summer schedule yet. I don't think I will be. I might. It seems like most summers I do teach it.
Teach 113?
113. But I haven't made out the schedule yet, so I don't know. Huh?
You don't know for sure yet?
I don't know for sure, but there's a fair chance.
Well, if you do, will you run my name now for that class?
Okay, you have to register, okay?
Okay.
But it's not out there yet. Yeah, we're working on the schedules this week.
Okay.
So as soon as I'll know, as soon as it's out there, you'll know.
Yes, sir.
Yeah. Yes, sir.
You know that paper they do for you?
Uh-huh.
What is that off of? I forgot.
What is what?
What is it based on? Like we got right on.
You pick your topic. Anything that has anything remotely to do with pre-calculus stuff.
Okay. And you want to write about why we like it?
No, I mean, you have to get outside source. You know, it could be a person, it could be a theory, it could be, you know, a principle, it could be an application. Anything that would apply to what we're doing in here.
Okay. And how long has it been?
1 to 2 pages,
Okay.
double space.
Okay. Thank you.
Okay. Do you know, let me see if I can remember his name. Harrison Boozer?
Yes, sir.
It was he a first baseman or?
Oh, he's a pitcher.
He's a pitcher, okay.
Yes, sir.
Yeah, he's in my calculus class.
He is?
Yeah, right.
So he's on baseball campus?
He's what?
He's on baseball campus?
He comes here on Mondays and Wednesdays at 9:30. Right. Yeah.
He pitched yesterday.
He did. You did. Way to go. Okay, I'll congratulate him tomorrow.
He did good.
All right, super. Thanks.
I called yesterday.
Yeah, I figured you were the catcher that you would know. So, yeah, does he throw pretty hard?
Yes, sir.
Right or left?
Lefty.
Lefty. Good man.
91, 90.
Oh, wow.
He throws hard.
Wow. He's a big guy.
Yeah, he's tall.
Yeah, okay, good deal. Your hand sore? Is your hand sore?